Hello, my name is Tim Luce. I'm the Chief Scientist of the ITER organization, and I'd like to thank you for this opportunity to present to you today at the Energy Meet the ITER project, opening the way to a new energy future. The ITER project is focused on fusion power. What is fusion? Fusion is the energy that drives the sun and the stars. It occurs when two light atomic nuclei get very close to each other. They combine, they form a heavier nucleus, and they release energy. And the challenge for us is to reproduce the fusion that happens in the sun and the stars on Earth for baseload energy supply. How will we do that? Well, first, what's the advantage? You can see in the first line here that 1 gram of fusion fuel ends up making the same amount of energy as 8 tons of oil. The ITER project uses an approach called the tokamak, and I won't go into the details for that, but it's a Russian acronym for a toroidal chamber that has magnetic coils. We start with a deuterium and tritium plasma. What are deuterium and tritium? They're isotopes of hydrogen. They're heavier versions of the normal hydrogen that we see. We heat this up in principle to more than 150 million degrees. This makes a plasma where the gas is separated into its electrical components. It's now charged, and we can hold that plasma in place by confining it and shaping it using strong magnetic fields. We then, as the temperature goes up, the fusion reactions occur, and we get what's called a burning plasma. And the word burning comes from the analogy of a standard wood burning or coal burning power plant, where once you've ignited it, it continues to heat itself and burn on its own. We don't completely burn on our own, but we get largely sustained reactions from self-heating from one of the fusion products, which is a helium atom. The other product that comes out of the fusion reaction is a neutron, and those neutrons transfer their energy to the blanket, and once they're in the blanket, they release the energy there as heat, and in a normal fusion power plant, a conventional steam generator and turbine set would transform that heat into electricity. So what's the attraction of fusion? What are the advantages? It will be a large-scale and predictable baseload power, which is complementary to renewables. It's safe, environmentally responsible. There's virtually unlimited fuel for thousands of years, and the fuel is globally distributed. There are no CO2 or other greenhouse gases released in the reaction, and there's no long-lasting radioactivity or radioactive waste produced by the reactions. So the energy issue is a global challenge, and in terms of fusion, we have a global response. The flags that you see here in front of the ITER tokamak complex represent the 7 partners of the ITER project. China, the European Union, India, Japan, Korea, Russia, and the United States have all joined together to form the ITER organization and the ITER project to try to realize fusion energy for Earth. This is a multinational scientific collaboration that has no equivalent in history. How will we do this? Well, as you can imagine, since it's new, it has a unique formula. ITER is being built largely through in-kind contributions of the 7 members. So almost 90% of the ITER facility is being delivered by goods manufactured within the member states. This has the advantage of tying the members together, but also they realize the advantages of the learning curve of manufacturing within their own countries. As the host state, Europe's share is larger because most of the direct spending benefits are within the Europe, and so they have a larger share of the cost in terms of the construction and manufacturing. What is the ITER mission? Well, as I said, we are looking for fusion energy, and our goal is to demonstrate both the scientific and technological feasibility of fusion power for peaceful purposes. And how will we say that we've done that? Well, there are 2 principal scientific objectives for the ITER project. One is to achieve a power gain of 10 a thermal output of 500 megawatts for 50 megawatts of heating input power, but also to explore in principle steady state operation at slightly lower power gain of about 5. What is the ITER tokamak? Basically, it's a large magnetic cage. We make the magnetic field with superconducting magnets inside a large vacuum tank to confine and shape the plasma. What we mean by superconducting here is there's no energy loss, but to achieve this superconducting state, the magnets have to be held at temperatures that are just above absolute zero. The magnetic set is shown here. First, the large magnetic field that goes around in the toroidal direction, the long way around the donut, is made by 18 toroidal field coils. Each of these coils is 17 meters high and weighs about almost 400 tons. At the heart of the tokamak is what's called the central solenoid. This magnet changes its current in such a way to make a strong electric field and drive current within the plasma. It's about 13 meters high and weighs almost 1,000 tons. Finally, the magnetic fields that are made by the coils outside of the tokamak, called the colloidal field coils, shape the plasma and make sure that the heat exhaust goes to the correct location within the vacuum vessel. So how does it all work? This is an overview of the tokamak, the ITER tokamak, shown on the left. We introduce fuel into a high vacuum container. We make a large electric field that creates a plasma then that carries a large current up to 15 million amperes. We heat that plasma with both electromagnetic waves and inject high energy neutral particles, and once we've used these heating techniques, the temperature needed for fusion is achieved. What's the timeline for the ITER project? Well, we've taken a staged approach to reaching this burning plasma, and this was done in a rebaseline activity in 2016. The schedule and resource baseline to first plasma in 2025 was set consistent with both the members' budget constraints and the technical capabilities to achieve the first plasma. In terms of the licensing requirements, we don't introduce the fusion fuel until 2035 when we have the full license from the French regulator. But we have 4 steps along the way, which are the first plasma and then 2 each of the pre-fusion power operation phases, where we commission the systems that are necessary for the final fusion power operation phase. The revised construction strategy is a very detailed timeline for how the tokamak will be built. I'm not going to show you any details here, but just to say that the critical path for that goes through the assembly of the core tokamak itself. And you can see at the bottom the 2 key elements are the cryostat closure in 2024 when we can begin commissioning the equipment, and finally leading to first plasma at the end of 2025 by our reference schedule. So I told you that the members bring almost 90% of the ITER facility in kind. This shows a picture of the tokamak with the contributors of the various components of the core tokamak assembly itself. And you can see that from the flags, it's a joint effort from all the members to make the core components of the ITER tokamak. One of the key features that's attractive to the ITER members, though, is that all of the ITER members share equally in the intellectual property that's generated. So for the members who are not the host states, they're contributing less than 10% toward the construction, but they get 100% of the intellectual property that's generated through that. So I'll give you some pictures here, an idea of what the manufacturing progress is. It's a global effort. I just show one example from each of the member states here. You can see in the upper right, the Indian member is delivering large components that make the cryostat. And the lower right, Japan is making several of the magnets, about half of the magnets. And you can see a picture here, the scale, how large these magnets are. The engineering team is standing fully inside the magnet structure that's completed. China has done a lot of work on the superconducting magnets also, and the feeders that bring the current to drive those magnets. Europe, the example shown here, is part of the vacuum vessel. Korea is also building the large vacuum vessel structures. They've delivered the first of kind already to the ITER site, and 3 more are coming in the next years. Russia is also making some of the magnets and some of the feeders that give the current to those magnets, but also some of the power supplies that are involved. And finally, the United States is also making the central solenoid magnet, the core of the machine. You can see here in this picture that we've made significant progress in the ITER project over the last 6 years. On the left is a picture from 6.5 years ago. You can see that there are very few buildings on the site. These were actually buildings that were from various members to assemble parts of the ITER components, and only the headquarters building existed from the ITER project. And then from a few months ago, the picture on the right, you can see the facility has changed substantially. Over 75% of the civil works now for the ITER project are complete. We recently had a celebration of the start of the machine assembly. You can see at the end of July, the pictures here, it shows that we had a virtual ceremony. Due to the pandemic, we couldn't have people so much on site. It was hosted by the President of France, Emmanuel Macron, and we had contribution from 7 ITER heads of state. But we actually started the assembly 2 months before that, and the key crucial milestone is shown here with the lift, one of the heaviest lifts we actually have in the ITER project, of the base of the cryostat from the assembly building into the tokamak pit, which I show here. So this is a lift down of about 50 meters from peak down to the bottom of the pit. You can see it says that the cryostat base is 30 meters in diameter, and yet it was placed into position with a final tolerance of under 3 millimeters at all the measurement points. This was a very significant achievement for us at the start of the machine assembly. On top of that comes the lower cylinder. This was lifted at the end of August and put into place, and even as I speak, the welding to connect that between the base and the lower cylinder is being done by automated robot welding. The first sectors will be assembled beginning this year. What's shown on the left is the first vacuum vessel segment. You can see the schematic on the right shows what it will look like when it's put into the assembly tools, which are behind it on the left picture. So those tools are special tools made to bring the toroidal field coils onto the vacuum vessel sectors, put all the fixturing so it can be lifted into the tokamak pit, where they're then welded all together. It's impossible to build the tokamak either fully in the pit or outside of the pit and then lift it in because it's too heavy. Finally, what's going on in the rest of the plant? As I told you, the superconducting magnets have to be kept quite cold, and the way we do that is to make liquid helium. And so we have the world's largest single platform cryogenic plant to do that. In operation, almost 25 tons of liquid helium will circulate when the tokamak is in operation. To reject the heat, we have a large cooling water system. You can see that over 1,000 megawatts of heat can be rejected by these cooling towers. So what are the challenges ahead for ITER? These come from a presentation made by the Director General a few months ago. The key thing is for us to continue working globally as a one ITER team, especially during this pandemic. We have some unique challenges we have to overcome. But as you can see, that even in this last year, we've been able to begin the machine assembly with deliveries onto site of the major components. We have a high set of requirements for both quality and safety. It's a very complex project, and the integration of the assembly and construction sequences remain a challenge for us. Beyond that, we have to make all the systems work, and we have to integrate them to work together on schedule. And finally, we have to operate and maintain it in a way that is consistent with the regulation by the nuclear operation regulations here in France. Finally, the timely and reliable availability of all the planned and committed resources from the members is key. So finally, this is a picture of the ITER site. I'd like to thank you for your attention. Our goal is to move onward toward first plasma in 2025, And I'm happy for this opportunity to present to you the ITER project. So thank you very much.